he was appointed as team leader at the Center for Nanoscience and Technology at Polymer CNST of IIT Milan. In 2014, he earned tenure track at the same institution, and he is now a fully tenured researcher. He received that tenure in 2019. Some of his research interest is solution-based high-resolution printing techniques for microelectronic, optoelectronic, and thermoelectric devices, organic semiconductor-based field effect transistors in biomedical and or implantable sensors for healthcare. Among the awards and honors, he received ERC starting grant in 2014 and ERC consolidator grant in 2019. He has over 120 scientific publications and his H index is 39. With this brief introduction, I request Dr. Kairani to start his presentation.
Thank you. Thank you very much for the introduction. I will now share my screen. Okay, so yeah, thank you for the introduction and thank you for the invitation. I think it's a way of having virtual meetings. We learned that it's possible recently, and I think it's a very efficient way of also delivering talks and to get knowledge with what people are doing in all the parts of the world. So I actually like this. So I'm going to share with you today what we have been doing in polymer field effect transistor recently, well, in the last few years, and especially in the delivering devices that can be printed or direct printed with techniques that are compatible with manufacturing, and delivering devices that are capable of high switching speed, so that they typically are faster than what we typically consider for organic electronics, which is still considered by most slow electronics for many reasons. I come from IIT, which is sounds like Indian Institute of Technology, but it's our let's say similar institute is Italian Institute of Technology, and possibly it was not a good pick of the name when they decided, because the IIT Indian was already there. But anyway, now the name is IIT also here. So my presentation is going to be our work dedicated to the use of conjugated materials, conjugated carbon-based polymers like this one, that can be solution processed, and day by day you use the techniques like spin coating to deposit thin films. And then we move to desktop printers in the labs, different techniques to print these inks and develop electronic devices with the aim to reach a maturity that allow us to scale to other pre-industrial or industrial techniques. This is an example of flexography printer with, from a local company in near Milan, Omer, that is developing printing machines for labels packaging, and we tested in the years the technology for printing electronics. So we talk about this also later. So actually, this is the first example of a technology transfer that we did. At that time, when we started this development, we were interested in testing this converting machine technology for photovoltaics. And in 2016, this startup company, Ribestec, we created it with the aim of delivering indoor photovoltaics. Basically, these are not for power plants, but these are for energy harvesting in order to power distributed electronics. Already existing electronics running on batteries is low power. There's a lot of cases of low power electronics. I mean, sensors for domotics, beacons, and other kind of devices. And in future, also plastic electronics could be another target. This company is now hopefully delivering the first product for on the market. And they are in independent premises, and we are hoping to see the first products on the market. So this, as I was mentioning, this basically this panel is photovoltaic panel can be a power source, a battery-free power source for also printed circuit. Okay, so if we substitute existing electronic with printed circuit, we can have some logic on a thin plastic film. And to do what? Basically, one example is to control, sorry, an actuator and a display, a simple display like an electrochromic display, in order to add functionalities to labels, for example. And this is thought, but the example that you see is a graphical example, is thought for marketing. The idea is that you can add dynamic elements into a label that is typically static. And you don't need batteries for that, because you see the dynamic, you need to see the dynamic element only where there is light, and where there is light, you can use the photovoltaic panel to give enough power to allow this blinking, for example. But this obviously it can be a platform to introduce further functionalities on common products. Okay, so the electronic that we have been developing to achieve this kind of goals is based on devices that are now quite well known. These are transistor, field effect transistor. This is a cartoon, a sketch of this device. We call it top gate and bottom contacts, and there are many materials now nowadays that you can choose from. These are, I'm showing let's say, these are materials from 10 years ago, but we are still using most of them. These are donor acceptor copolymers, for example. But these are semiconductors that gives good properties and good performances, and enable quite well-performing devices. And just to show a routine process that we use in the labs when we develop these materials, this is from years ago, but anyway, we have similar processes now. We can use inkjet printing, for example, to pattern electrodes in a polymeric conductor, PEDOT-PSS, and we can use inkjet then to pattern the semiconductor in the channel, your semiconductor of choice. You can come with a large area coating technique, like bar coating or knife coating, to coat the dielectric, and then you can inkjet print the top gate, and you have your full transistor built from scratch. Obviously, this is, and you find an image here where the channel is 100 microns, but you can get a little bit shorter channels, like 50 microns or so. But with the resolution of inkjet, this is more or less the resolution that you get with state-of-the-art tools that you can easily buy. Nevertheless, still the resolution is low, but you can make complementary devices by picking the right semiconductors. You can make P-type and N-type devices, and therefore you can enable complementary logic, which is the one that we favor because it's much more robust than unipolar logic. Okay, so we can do this kind of complementary logic. One issue you see immediately from these graphs, which are from publication a few years ago, we are running these devices at tens of volts. This is not acceptable for applications, because for application we either want to use thin batteries or photovoltaic harvesters, so we have only a few volts, and therefore we have to work on this dielectric. The issue here is very well known. We are using dielectrics, which are low-K polymers like PMMA, and we make them very thick, because when we coat, it's very easy to have defects, and therefore, and pinholes, and therefore you need to have thick layers in order to avoid leakages and breakdown. But this is not acceptable for operation voltages. So we developed several ways of lowering this kind of voltages. This is one example, which is an hybrid, based on an hybrid process. So we have, this is a capacitor, metal insulator metal, where we have a very thin, it's a very thin PMMA layer, so the same low-K polymer, but extremely thin. This is not acceptable at all for application on its own, because it's going to be extremely leaky. And we coat on top a Parylene layer. Parylene, it can be deposited at room temperature through a CVD process, and it is already industrially scaled. And it's very, it's basically considered a pinhole-free layer. So this double stack which is has a thickness of just above 100 nanometers, can easily reach aerial capacities of tens of nanofarads per square centimeter, which is 4, 5, 6 times higher than what you can get with typically low-K polymer, half a micron thick. And you can reach low leakage as well. You see here we have nanoamps or tens of nanoamps of 10 volts. So we can use this kind of stack, and in the same device that I showed you before, replacing the thick PMMA layer, and still it's important to have this low-K polymer dielectric in the contact with the semiconductor to take care of the energetics of this interface, which is very crucial. And we exploit the full stack instead to have low leakage. And you can see the characteristic curves on the right of the devices. The leakages are very, very good and under control. The processed in a lab scale process, obviously, this is not a fab, right? A fab process. It's high. So if we make 100 devices, 99 works in a research lab environment. And this, importantly, now works at below 10 volts. We don't need, you even work down to 2 volts. So this is compatible with many other power sources. And so you can use now these complementary devices to make the circuits. And so you can make ring oscillators, and they oscillate down to 3 volts or so. They are very slow. Obviously, we have now reduced the voltage of operation, but the resolution of the printing is the same I showed you before. The mobilities are in the range between 0.1 and 1 square centimeter per second. So you cannot expect here high switching speed, but they work. And you can make more complex logic circuits. So basically, flip-flop is one bit, let's say, one dynamic bit that you can use in the shift register, for example. And you can see the photograph of its realization here. And this can work as well down to a couple of volts. And you can use this element then to start building some useful circuitry, like this is an 8-bit shift register. It's used in serialization in RFID tags, for example. And they are already, this is interconnected with very simple fused memories that you basically just open or short circuit, and so we can exploit this kind of technology to make these applications, and compatibly with the voltage that can come from again from thin-film batteries, from a rectifier, for example, if you're rectifying an electromagnetic wave through an RFID antenna and so on. So this was the base for creating another startup company, Flipec Technologies, that where we transferred the part of this know-how. And what you are seeing in the video, it's not very clear. Anyway, it's a fully printed 2-bit counter with a decoder and with the necessary electronics to run the small LEDs. With another company, we explored applications of this technology to biomedical devices, very simple, like inhalers, where you don't need sophisticated electronics. It's not you need very simple functions, like counting the discrete events, how many times you have expelled the chemical. You can do very easily with a mechanical counter. You can do very easily with a silicon chip, obviously, right? And an LCD display. But these things change completely the nature of this object. This object is the inhaler, the original inhaler is a mechanical object. It's extremely cheap in the shop because it has a specific shape. It's producing millions of pieces. If you change its shape, you integrate an element like that, the cost shoots up. So the idea was, why don't we use a label, a very simple label, well, the same label we put on the canister, why do we don't integrate a counter? So that basically you are not changing the process flow of these objects, and you don't add too much on their cost. So this is why the multinational company Flex, they have a design center here. They were interested to study this kind of circuits to integrate in the label with us. And these are other examples of applications that Flip Technologies, and these are the two guys that work with me, Giorgio, now CEO, and Paolo, head engineer, are taking along and hopefully develop in the near future. So now coming to the frequency. So these devices are working, can be used to make counting, for example, so they can be used to count discrete events. Are very, very slow, right? But they are not suitable for high frequency application. They're too slow. So, and typically, this is how, I mean, this is just a picture of parasitism and the frequency of transition to describe the figure of merit I'm going to talk in the next 10 minutes. So we use a typical frequency of transition, a figure of merit, to determine which is the highest possible frequency at which you can operate a device, a field effect transistor. And this comes from the transconductance of your device. You want that to be as high as possible. The transconductance translates the voltage, AC voltage you apply on the gate into an AC signal in the channel, and the parasitic current that you are injecting anyway in your device when you are stimulating the gate, because you have gate to drain and gate to source overlap. So you have capacitances, and you are injecting a current in frequency. When this current, the tail current, becomes higher than the channel current, you don't have a transistor anymore. It's a capacitor. You don't see the transistor. So we define this corner frequency, if you wish, below which you can operate your device as a transistor, above which you don't have your transistor anymore. So FT is this figure of merit. The strong source of parasitism is the capacitance between your metal or your conducting gate and the source and drain electrons. And you want to get rid of that. Okay, this is other ways of showing the same FT. So if we measure the device, at the beginning of the presentation, I showed you fully printed devices with the 3MMA stack. If we measure the FT there, we get, with materials polymers that have mobility in the 0.2 square centimeter per volt second mobility, you have frequencies in the range of tens of kilohertz. But that's the maximum you can achieve with this channel length and with this parasitism. But interesting, it's not the channel length, the mobility, which is limiting the frequency. Even if it is, this is already a first thing, it's the capacitance already. Even for slow devices, the capacitance is a killer, because we are depositing very large pads with big capacitances. So we envisioned a few years ago the possibility of working a lot on these devices, on the architecture, on the way we were introducing materials, and so on, to bring these slow electronics toward further applications. So if you want addressing electronics for fast images, or plastic image, or for displays, even more, or for wearables. If you want, if you have a large area sensor that you print and it's low cost, but you want to transmit data, how do you do? Well, you have to attach a silicon chip, and that costs you a lot, but not the silicon chip, which doesn't cost too much. It's the integration itself. And therefore, it would be useful if you could do some local area transmission, for example, of data short range with some printed electronics. Okay, but you have to move the frequencies up of orders of magnitude, close, even thinking of a gigahertz. And that's what we started to do by working on all the aspects of these devices. So patterning resolution to have a shorter channel, dielectrics, mobility of semiconductors, and so on. Just to give you an idea, if you just, what we realized in the years, that there are ways of depositing, of coating the polymer semiconductors, that it strongly improves the mobility and therefore the transconductance. For example, you can use shear stresses that you impress with bar coating, for example, if you choose the right solvent for some of these donor-acceptor copolymers that are known to aggregate already in solution, to stable aggregates, where we are able to orient very easily the fibrils that are formed by these things when they are in the solid state, and you can induce anisotropy in transport and strongly improve the transport in the perpendicular direction to contacts. You can strongly improve the transport and induce the scattering of the data. And here a simple proof of concept. If this is a simple device where the short channels are made by lithography, 5-micron channels, but we either use spin coating of the same polymer, so no preferential orientation, just a spin coating, and we use bar coating to align the polymer. You see, we can gain an order of magnitude in transconductance, and therefore in frequency of transition. The capacitance obviously is the same because the architecture is the same. So this allows you to enter immediately megahertz regime. Then we didn't want to use lithography for our devices. We tried to find ways of reducing the channel length by combining printing and dry writing techniques. Especially, we are making use a lot of femtosecond laser writing. And this is compatible with plastic substrate and with organic semiconductors. This is one way of making a short channel. You can inkjet print your metal. For example, this is silver, and then you cut with a laser a very short channel. It can be even submicron if you wish. Since you're using femtosecond laser, you can exploit a different threshold of ablation of materials, and you can deposit energy only in the focus. And you are not melting the surroundings. If you try to do this with longer pulses, it's very difficult. You need to manage it much better. Yeah, you can do on the very same substrate you need for your devices. This is an example where instead of silver, we used PEDOT-PSS, which are polymer conductors, and we use infrared light to cut slightly longer because we are using a longer wavelength channel. So this channel is in between 1 and 2 micron. And you can see here, and then the processes are very same as the one I showed you before. You inkjet print semiconductor, you coat the dielectric, and you inkjet print the gate. And this is the final. You can see there the final device. Well, this device is not, it works, but it's not optimal for parasitism because we are now trying to gate a channel which is 1 micron long with a gate which is 100 micron in width and overlaps a lot with source and drain for a very short active area. So what you can do is just a little bit of engineering. You use instead an interdigitated structure so that the overlap of the gate with source and drain intercept a lot, a wider active area. Okay, and so this rebalances a bit the ratio between transconductance and the parasitic capacitance. And with this solution, you can achieve with a completely organic field effect transistor made of plastic with just that, without masks, you can achieve a few megahertz, so 5 megahertz almost operation. Still at quite high voltage in this case, 30 volts. So this kind of processes we are now trying to transfer, and we are collaborating in a local regional project in Regione Lombardia to transfer this femtosecond patterning onto a R2R printer, the fixography printer I showed you at the beginning. The idea is that there is some skepticism of using femtosecond patterning in industrial environment because you may think it's slow, but it can be parallelized. You have much more power than you need to do these kind of ablations, and you can have galvo scans to scan very fast the beam or the beams over a web of a printer. And we are now developing these tools, and we are firing the first laser cuts on these tools in these very days. And this is within a regional project where we aim to transfer this kind of processes to companies to integrate electronics into labels and packaging and so on. It's called the iLabel project. So another way of using the laser to do similar improvement is to instead use a local sintering. So you can use an ink, a precursor of a metallic electrode, like a silver nanoparticle ink. You can coat your substrate, and then instead of hitting it on a hot plate, right, and you would have the full sintering, you can come with a femtosecond laser again and write basically micro scale lines that are an order of magnitude at least lower than what you can get with the inkjet printer. And you can, and the trick again here is to use a wavelength which is not in linear absorption, so it's not absorbed by the ink in linear absorption. So you can exploit multi-photon processes, and you depositing energy very precisely where you need and control the size. So this process is compatible with plastics substrate as well, with glass, plastics. And on top of these electrodes, we realized structures with, in this case, fully solution process dielectric stacks. So we exploited the same double layer strategy I showed you before, but using cross-linked interlayers and the high K and some high K high K solution process polymers on top. And so we can have devices with short channels down to 1 micron that are run at a few volts. And with this, we showed that it's possible to access megahertz operation already on plastic, already at 2 volts. And we got a highest frequency at 14 megahertz with only 7 volts. This is promising already for some application. For example, if you use one of these transistor in trans-diode configuration, so basically you short circuit the gate and the drain, and you make a diode, you can use this as in a rectifying circuit. If you have a transmitter that sends an electromagnetic wave at 13.56 megahertz, for example, which is a standard, you can stabilize a DC voltage on your plastic substrate with your direct written rectifier. And this is useful, obviously, to deliver power to any kind of substrate. This is one example. And actually, we realized the same component, which is very important component, the rectifier, for if you think to RFID, is also with vertical diodes. This is just to give you another example. There are no transistors here. This is a vertical diode. We use similar materials, and we make a very simple full inkjet printed diode. So silver, then a charge injection layer, and a semiconductor silver, and we got very good rectifying diodes that can operate up to 25 megahertz, and we use these rectifiers also to power some circuits. And obviously, you can use what I showed you so far to basically build with fully printed techniques some passive RFIDs. You can use a 8-bit shift register for the serialization of bits. You can have a rectifier, printed antennas, and so on. Okay, so coming back to frequency of transition and to go to the conclusion of my talk, one issue that we faced in the lab was when we were using basically DC or quasi-static techniques to characterize frequency of transition. And this is okay, and you can try to measure parasitic currents and channel currents in AC up to a few megahertz. But then it becomes impossible, and you have to switch to very well-known engineering techniques to extract, to do AC characterization, but seldom used in organic electronics field. And like, for example, S parameters. This is used for any AC characterization of high frequency devices in other inorganic technologies, but was used, for example, only one time before by Hagen-Cloud in Stuttgart in collaboration with the University of Stuttgart. So we decided to develop in our lab these capabilities because we wanted to push our devices higher and higher in frequencies, and we had to do this step. This is just to tell you that we have these capabilities now. I'm not going into the details. The things that you are using, you are sending a wave, and you see the reflection of that wave, and you extract some parameters, and you can remodel it and understand what is the frequency of transition. Frequency, and this is the first case where we used with our devices based on printed polymers and laser sintered electrodes, and we used successfully these techniques to extract the frequency of transition up to 19 megahertz for printed polymers. Very last and very recent result. We are not published yet, but it's under revision. So we put together all the techniques basically that I showed you so far. So we tried to make the best of what we developed so far. We made the laser sintered contacts. We made the best semiconductor that we could control, a fully solution processed dielectric. And then we aligned again with laser sintering the gate, fine gate aligned on the channel to reduce the parasitism further, and this to achieve the best possible frequency of transition. And this was the result. So we now are able to develop devices that work above 100 megahertz. This is 160 megahertz for a device based on a printed polymer, and this is the record for organics. And we are quite happy of that because, you know, at 300 megahertz, it starts the ultra high frequency bandwidth, where we can really start to use these devices to transmit information. The limit in what we have been doing so far, still you see the voltage for this kind of high frequency device is still high, 40 volts. We have to reduce that, but there are issues in doing that. But obviously we are working on reducing the operation voltage of also this high frequency device. And the other important topic we have really seldom discussed is that we have to use, in this case, we could not use a plastic substrate because our devices were melting. If you try to run these devices, they undergo a temperature breakdown, meltdown. So there is a positive feedback. They heat up, since the temperature is higher, they conduct more current and they get warmer and warmer and they blew up. So we had to use a substrate with a sufficient thermal conductivity. We chose, just to prove the concept, aluminum nitride. But this is a very important aspect if we want to maintain flexibility. We need substrates that are able to manage heat. Obviously, when we will lower the operation voltages, also the power will be reduced. These issues will be a little bit mitigated. But still, this is heat management is indeed one issue we will have to face in the future. So with this, I've concluded my presentation. I hope you find some aspect of interest. And anyway, I showed you that with state-of-the-art printing tools plus high capacitance dielectrics, you can make complex circuitry, and because you can have processes with high yield and low voltage transistor, and therefore you can start to make interesting applications, and we are trying to do that. And if you then couple laser-assisted micron-scale patterning, you can make low voltage devices that can operate on plastic thin films above 10 megahertz. And to show you that it's not a limit, the limit is not on it's more on the architecture of the devices rather than the physical limit of charge transport of these devices. And so if you work on that, you can push these frequencies much further. And we are now above 100 megahertz, and we are working on increasing this number even further. So thank you very much for your attention, and thank Lisa. Well, it's last year pick of my group, and a lot of people involved, and I have to thank them. And so I'm very happy to receive questions. Thank you very much.
Thank you, Mario, for a very informative talk. Some questions are there, so I will just put forth. So the first question is that what is the high K dielectric layer thickness in case of your megahertz FETs?
Yes, we have several of these dielectrics. The solution process stack, we have tens of, the first layer is 20 nanometers or so, and it's a cross-link. The cross-linking we use to make it very robust to the second layer, where we pick a high K dielectric, Tilpululan, for example, and that's a couple of 100 nanometers at least.
So with inkjet, you can get 20 nanometer thin film?
No, sorry, the dielectrics are coated. We never use inkjet. We don't use, so far we have never used patterning techniques for the dielectrics. We use coating. We typically use spin coating when developing, or we use bar coating when we want to go more larger area. But it's a coating technique for dielectrics. Yeah, with inkjet, I think it's more difficult.
Yeah, so thank you. One more question is that so what is the application? Let's say these devices are high frequency FETs. So can
Yes.
you just give us some application area for like common people who want to understand the
Yeah,
application
sure.
area for?
So I mentioned a few. So if you think about common objects that anyway people are developing, like there are these plastic images. What are plastic images? Are arrays of diodes or organic diodes on a flexible substrate, and you want to use it as images, for example, for X-rays. But if you want time resolution, maybe not for X-rays, but for infrared, for security, you need addressing electronics, for sure. Addressing electronics mean electronics that can control the rows and the columns. And that has to be compatible with the frame rate that you want from images. So your single transistor must switch at much higher frequency than what we typically get with normal tools. So, and there you need at least tens of megahertz. Okay, so you need to be at least in that range. And that's the same thing for displays, 10, 100 megahertz, that range. Above, why we want to go above? Well, again, I mean, the example is really if you want to wear a sensor, an ECG sensor, pressure sensor, temperature sensor, where do you send the information? You can put cables, but, well, that's limit, especially on the body. Or you can put a silicon chip to transmit the information. And you can use it very easily. But obviously, you have to take care of different materials with different young modules, right? The one is very thin and conformable, the other is rigid. You have to do so. The aim here would be to have a circuitry which is capable of replacing, for this function only, the chip to be able to send information to a local gateway, your smartphone, for example. So very local info. We don't think it will be possible to broadcast any long-range information. But local area networks, where you can use the very same printing technology that you use for sensors, also to transmit locally the information. Then some silicon device will take that information and do all the complex stuff beyond. At least this is the idea and the vision we have. We will try to develop some proof of concept of these applications.
Sure. So just last couple of questions, then we will close this session. Actually, if there are further questions, I request the participants to write here. I will forward those questions to you by email. Maybe they can contact you through email.
Absolutely no problem. I'm very open to that. Yes.
Okay, so the question is that that N-type had contact resistance and
Yes.
more than the P-type. So is there any problem for circuit analysis? And why do you choose the top gate structure?
Okay, so start from the last. Top gate structure for us, it's always have been an easier architecture to optimize our devices. Since you can use a little bit of the overlap between gate and source and drain, which is a parasitism in some terms, but is also helpful for injection. Okay, this is part of the story. We use that, and it's easier for us to optimize our materials. If we put these donor acceptor copolymers in bottom gate, bottom contacts, it's much more difficult. Although, if you look at Hagen Cloud's recent papers with small molecules, evaporated small molecules, it could show that in some very specific case, there is no advantage in using top gate. But there are very specific cases, you need very high capacitance. Okay, but in our case, top gate, it's easier for optimization of devices. Regarding contact resistance, yeah, I mean, we still have some contact limitation, especially in the downscale devices. Let's say this is compatible anyway with the frequencies we have developed. We are constantly working on trying to reduce that. That is one of the bottlenecks of achieving even further frequencies. That for sure is the thing we have to solve, because people have tried to reduce contact resistance so far using techniques we did the same, that were developed 10 years ago, self-assembled, or 20 years ago, self-assembled monolayers, charge injection layer. I believe we need now something more, especially for N-type. Well, actually, in our case, also P-type is not perfect. And I think we need to develop some doping techniques, as it is done in CMOS, right? But we don't have full control in organics yet. And if we manage to scale down further contact resistance, we will be able to reach higher frequencies.
Sure. And the final question is that regarding the P-dot PSS as the source and drain electrode, is it a good choice in terms of stability is concerned? Because we know that it is a hygroscopic material and it can.
Yes, for stability, yeah. Let's say I've not explored in particular that detail, whether how important is P-dot PSS itself on the stability of the device with respect to everything else. What I can tell you here is that our devices, when we use obviously we need to encapsulate the devices, right? With flexible barriers. When we use commercial barrier materials that you can coat on top, we don't see degradation. We have not tested for a very long time, but we don't see degradation in a year or so. So we keep working. But I understand the point. I've never explored. So my answer is that you will need for sure to encapsulate.
Sure. So we will close the session now. Thanks a lot, Mario, for accepting our invitation. And we will probably get back to you for some suggestions and maybe a possible collaboration regarding these printable devices. So thank you.
Thank you very much for your invitation, and very happy to hear from you and discuss. Yes, no problem at all. Thank you very much.
Thank you. So over to Professor Cheralathan for concluding remarks.
So on behalf of Organizing Committee, I sincerely thank Professor Mario Cairani for joining us and sharing his research work. Thank you so much, sir. Over to Dean, ma'am.
So are we concluding right now, sir? Are we concluding?
Yes, ma'am.
Yeah. So at the outset, I would like to thank everyone for registering this virtual conference. And I suppose it was a useful platform where we learned so many things from the experts who shared their views as well as their research experiences with us. And at this point, I would like to thank all the speakers who have accepted our invitation and come forward to address through this online platform. I think it was very interesting and it was highly illuminating to all of us. So we were really attracted by your research field. And regarding the center, what we are proposing from School of Advanced Sciences, it is purely on devices fabrication as well as screening the application of various materials and nanotechnology, whatever we were doing in the experiments. So we are supposed to come out with a product which will be addressing to the real world problem as well as to meet with the society needs. So at the juncture, I would like to thank all the speakers for accepting our invitation. And we are all waiting to meet you in the campus when the situation is coming to the normal condition. And thank you very much once again. Again, I would like to congratulate the organizing secretary, Dr. Cheralathan, for accepting this task and having conducted this program in a successful manner. And also, I would like to thank all the committee members, the organizing committee members, the center members for their excellent cooperation in making this event a grand success. So thank you one and all. And I'm also thankful to all the external participants who have participated from other institutions, as well as the professors and scientists who have come forward to listen to this online platform, as well as for your contribution in listening, as well as registering for this wonderful virtual conference. So hope to meet you all again in the campus. Thank you so much. Thank you.
With this Thanksgiving note from our Dean, SAS, and Convener, Professor Mary Saral, I close the proceeding of this conference. Thank you so much. Thank you all.